Hello everyone, here is Orillusion. Welcome back to WebGPU tutorials. Last week we implemented 3 different basic WebGPU textures. And from this week we are going to learn how to add lighting. But lighting is not a specific feature of WebGPU. That is the basic theory of computer graphics. So today let me introduce some basics of lighting. In the real world, we see the color of an object is not the color of that object, but the color of the light it reflects. The object absorbs part of the frequency bind in the light, and then those frequencies not be absorbed by light will be reflected into our eyes. For example, the coral red balloon. We can see this because it absorbs most of the high frequencies in visible light. So the relatively low frequency light, the red part, has been reflected. And in the digital world, we can't simulate the natural light. We can only use some limited number. And the most common used is 3 primary colors, which is red, green, and blue, which is known as RGB color. So the combination of these 3 components can simulate most of the visible light. If we use the range of 0 to 1, then we can describe this red as 1, 0.5, and 0.3. And for the white light, it could be 1, 1, 1. So how to simulate the principal real reflected light? We're going to multiply the actual color of the light and the color of the object. And then we'll get the color of the reflected light that we can see. In this case, we are in the white light environment, so the color of the reflection is the color of the object itself. But if the color of the light is not white, let's say if we use a dark green, then the resulting color will be like this, a brownish color. In the previous demos, we didn't take into account the light factor, we just output the color of the fragment texture. But now we can start simulating the changes in lighting. The lighting in the real world is extremely complex. Given the current computing ability, we can't simulate the real light, especially considering the real-time rendering. You always use some simplified models to approximate changes in lighting, to simulate the real lighting as much as possible. And today we're going to learn some classic models. Now let's look into the phone model. It breaks down the light into 3 basic elements: ambient light, diffuse light, and the specular light. The final lighting effect of the object is the combination of these 3 types. Let's first look into the ambient light, which can illuminate all angles of the object, just like sun, moon, and stars, and the reflected and the scattered light from the surrounding objects. And they come from different directions and influence each other, so it is difficult for GPU to simulate this. Phone model just to simplify the complex light environment. We usually use a small constant to add it into the final color of the object. For example, we multiply a factor to all the fragments of this object, for example 0.1. And this will simulate a relatively dark light environment. As for diffuse, that is actually the direct visual effect from the object. Most of what we see in the real world is coming from the diffuse reflections, because the surface of the object is not absolutely smooth. So the incoming light will be reflected or scattered in all directions. It's very hard to simulate all directions, so we are going to use a phone model to do the diffuse reflection. And there is a light reflection component which is perpendicular to the surface. And we can measure the angle between the incoming ray line and the vertical direction of the surface. If the angle is smaller, then that means the light description is closer, which means that the object will be brighter. On the contrast, the larger the angle and the smaller the brightness. And in mathematical, when we calculate this angle, we use a normal vector multiplied by the direction vector of the incident ray. That is the basic knowledge of vectors. Dot product of two vectors equals to the length of two vectors multiplied the cosine of their angle. And if we set a unit length, then the result will be a cosine angle. And if the angle is smaller, then the result tends to be 1. And when the angle is greater or equal to 90 degrees, then the result of their cosine will be equal or less than 0, which means there is no light effect on this fragment. Then there is no reflection color. So it makes sense that we can use this cosine value between these two vectors to simulate the reflection brightness of each fragment. And if we apply this to all the faces on 3D objects, then we can simulate the overall light and shade changes. And now let's look into this vector calculation. And usually we do not calculate in the shader in real time about the normal vector. Actually, all the fragments in a triangle, they have the same normal vectors. So when we create the model, we'll calculate the normal vectors for each face, and then add it into the vertex buffer, and then pass into the shaders. As for the vector of the incident ray, is much easier to calculate. We can subtract from the spatial coordinates of the light source from the spatial coordinates of the current fragment. Now let's look into the specular reflection. We have an observer here. The incoming light will bounce back along the reflected vector, and if the angle of our sight is a smaller angle to this reflection direction, then we'll get a greater effect of the specular reflection. And that is the highlight effect of an object. And the calculation is similar to the diffuse reflection. We just need to calculate the angle between the light and the normal vector. Another one is to calculate the angle between the reflected light and the light of the sight. We are going to use the position of the camera to get the set viewing direction. It may be a little bit complicated, but here we just need to understand the process. And besides, in actual implementation, to simulate the different reflection intensities, and we're going to use the n-cephers to increase the decay of the cosine. That is also known as shyness. So the larger the n value, then it means the greater degree of attenuation when we shift the viewing angle. And actually, we can set different factors to the ambient light, diffuse, and specular reflections to simulate the materials of the object. And that will result in different lighting effects. And here is a summarization of the lighting parameters of many objects like jade, gold, and silver. And of course, in practice, we'll not set a single value to simulate the materials. Usually, the object will contain multiple materials. Some part may be rough and some part may be smooth. So the scattering and the reflection is also different. So in this case, we're going to use a light map to make fine the lighting settings. For example, these two light maps. We want to rendering a wooden box with a steel ring border. And the textures is actually the diffuse reflection map. But the reflection of wood and metal is different. So we need to set the specular light settings individually. The wooden part in the middle can be completely black, which means the corresponding colors are 0. And we only set the color for the border part. And the lighter, the whiter, that means we have more specular reflection. And this is the specular map. The red figure is diffuse only effect now. And if we composite the specular map, then this is the new result. The wood part is not reflective, and only the frame is having the specular highlight. Now we have a more realistic light effect. And in the real complex scene, then apart from the diffuse reflection and highlights, then we can also use the normal vector shadows, reflections, and other data to set into the texture. And there are also many other lighting algorithms, like Lambert and physical-based rendering. Lambert models will ignore the specular effect and only consider the diffuse reflection. This model is simpler than phone, but more effective. And PBR will use more complex light model to have a more complete reflection algorithm, and considering the reflection and scatterings from other objects. But the cost is also very large. With the improvement of GPU, more and more PBR is implemented. Apart from the materials, the light source itself will be an important factor affecting the final effect. For example, the most common parallel light or directional light, similar to sunlight. Because the sun is too far away from the earth, so the light can be approximated as parallel light. So we can use this to simulate the global light of a scene. And another light source is point light. It has a location and it will glow in all directions, and we generally use this to simulate the light bulbs. So we need to calculate the direction of the incident line according to the different fragment positions. Generally, the light will attenuate a long distance. We also have many different attenuation algorithms. The most simple one is a linear attenuation, but this is a little bit fake. And for beginners, we can use the attenuation by the square of the distance. And now let's look into the spotlight. This is gonna simulate the flashlight. And the light source is only set in a range of directions to form a conical space. And only objects within this cone will be illuminated. And in order to simulate a real lighting effect, we're going to do the attenuation along the distance. Also, some optimization algorithms along the conical edge to do some smoothing to make the spotlight more realistic. And we are going to implement this in the next video. In the real scene, the objects will be affected by multiple light sources at the same time. Then how do we calculate the color of each fragment? Actually, it's very simple. We just add different colors of multiple rays and calculate them in the separate shader. In the rendering process, we'll go through each fragment, and then for each fragment, we'll go through every light source in the scene. According to the different properties of each light source, we're going to calculate the colors. And then we put these colors together. This is also called forward rendering. This algorithm is easy to understand and is simple to implement, but the disadvantages is also very obvious, especially when the scenes contains lots of light sources, and there is some optimized rendering method. We will introduce them in the future. Okay, thank you for watching, and this is the theoretical part for lighting. And next video, we're going to implement the forward rendering to see the reflection difference between different light sources. Welcome to subscribe our channel. I'll see you next time.